Welcome everyone to this IAQM webinar, SmogStop, the world's first approved air quality barrier. We are delighted today to be joined by Dr. Andreas Kafasas. Andreas is a lecturer at climate change in the environment at Imperial College London and has been independently reviewing the work carried out by SmogStop. His research is focused on developing sustainable processes to produce photocatalytic coatings for a range of practical applications, including renewable fuels, air remediation and water remediation. As usual, after his presentation, we will have time for questions, so please do put these in the Q&A option at the bottom of your screen at any point, and these will then be read out on your behalf later on. Thank you so much for joining. Just to let you know, the webinar is being recorded and will be made available on the IAQM website and the IES YouTube channel for you to watch afterwards. Thank you so much, Andreas, for joining us today, and I'll hand over to you.
Oh, thanks for the very kind introduction. So this is what I'll be talking to you guys today about, this first approved air quality barrier. And the reason that I've been asked to talk about this barrier is because it uses photocatalytic technology. So to many of you probably joining this webinar, you may not be so familiar with what a photocatalyst is. I've been working on them for about 15 years now at university, mostly at Imperial College. So I should be well placed to inform you on what a photocatalyst is and why this is a new and exciting technology and how it can be used to combat our fight against air pollution. Okay. So this is an outline of what I'll be talking to you guys today. It'll be about my expertise and why I'm interested in this barrier, this SmogStop barrier, how I got involved, and why I think this is a very unique and exciting technology that they've developed. I'll be talking to you about the issues with NOx pollution from roadside traffic, which you guys will be already very familiar with, but telling you a bit about the targets that we need to meet. Then I'll go into the details of this technology, so that the R&D of the photocatalyst that's used in the technology. So that's where it gets a bit more technical, and I hope that I'll keep it understandable to the wider audience. I'm a chemist by training, but I'll keep it in mind that you guys will be coming from many different disciplines, so I'll try and keep it understandable. And then specifically how this photocatalyst can be used within this barrier to then fight NOx pollution at the roadside. Then I'll be talking about how it's been tested in Canada, in Toronto, in the field trial, and some of the outcomes from that trial as well. And then I'll wrap up and we can ask you, you can ask me questions. So this first slide, there's a bunch of words here. It's a word cloud. So I recently developed a new collaboration with people at other universities. In fact, actually, University of Toronto, it's a bit ironic. And I wanted to describe myself to those new collaborators in one slide. I thought a good way of doing that was to take all of the titles of the work that I've published so far. So I've published about 90 papers so far in my career. I took all of the titles of those 90 papers and I whacked them into a word cloud. And these are the different words that came up. And you can see there's lots of kind of chemistry words there. You can see them like titanium, chemical, oxidation. But the biggest word that came up was photocatalytic, which is to do with photocatalysts. So I'm big on photocatalysts. I really find them so interesting. And I'll tell you a bit more about photocatalysts and why I think there's so much to be done in this space, and it can be so useful in the future. So that's me in a nutshell, that page. And I've been working a lot in this field. And how did I get into the field specifically of NOx remediation? Well, I was working primarily on coatings just for like self-cleaning. Okay, so things that would just break down foreign organic matter when they land on them to keep windows clean. So I was working with a company called Pilkington NSG on enhancing their product, their self-cleaning product. I was also moving into the space of clean fuel. So there's this holy grail within the photocatalyst community of taking water and using sunlight to convert that water into hydrogen fuel. And that would be very clean, sustainable fuel for our future and help us combat climate change. And I'm still working on that technology. And then I heard about NOx pollution and how photocatalysts can also be used to tackle NOx pollution. So in 2017, I was approached by the Environmental Industries Commission, and they wanted me to review all of the work that had been done in this space so far. So photocatalysts for NOx. So I reviewed more than 100 papers on photocatalysts for NOx. And within this body of work, there was a lot of stuff done in the lab, and there was some stuff done in field trials all around the world. So there've been a couple of field trials already in the UK, and stuff in Europe and the US as well, and also a very big trial done in the Philippines. So really interesting. You can see it here. If you're interested in finding out more on what's been done so far, you can read this report. And what I found specific in that trial is that when you do things at scale, then you can actually start to see changes in ambient pollution levels in the air. So essentially, you can coat buildings, tunnels, tiles, windows. You can coat large areas of building materials that are already within cities, or connections between cities like highways. And I'll go into that in a bit more detail later. And if you can coat a sufficient amount of area with these photocatalysts, you can actually start to see within these large bodies of air that circulate around these barriers, you can start to see significant changes in NOx levels. And I think there was a field trial in the Umberto Tunnel in Rome, which is a very large stretch of tunnel, several hundred meters, that they were able to see significant changes in NOx levels on entering and exiting the tunnel using a photocatalyst there. And I'll go into what most people use as their photocatalyst and why SmogStop is so different later. But I got really excited about this technology. And then in 2018, I myself started working on developing photocatalysts for NOx pollution. So I developed a photocatalytic testing unit in line with the ISO for how photocatalysts should be examined for NOx. And we've recently started publishing some work, mostly focused on these really sort of nanoscale materials which have really high surface area that can photocatalytically convert NOx into something more benign. And I'll go into that in a bit more detail later. And now I've also started working with companies like Codecoat, Boyson, and others on advising them on how they can improve the performance of their catalyst. And sometimes using my facility here at Imperial College to certify the performance of their products. And then in 2021, I was approached by Steve at SmogStop to review their technology and assess its performance. So essentially, their barriers have been applied in a UK field trial. I can't talk about the data yet because we're about to publish that report. So that will be out soon. But it's one of the largest field trials that I've ever seen. It's one of the most elaborate, to my knowledge, in terms of the number of points across the barrier that are where they're measuring changes in NOx levels. I was initially tasked by SmogStop to independently review it, but after discussing the field trial with National Highways, now it's all a big collaborative effort, and we're going to do a joint report on. Like I said, it'll be released really soon. It seems quite positive from the SmogStop side, in the sense that what they predicted its performance would be, it seems to be coming out as that as well. So it looks quite interesting. So yeah, I'll go a bit about the problem of NOx, and then I'll talk a bit more about photocatalysts and how they actually work very soon. So we all know that NOx is a big issue. It mostly comes when you burn fuel, and the high temperatures at which fuels burn results in nitrogen and oxygen combining and making these radicals, nitric oxide and nitrogen dioxide. And they're really toxic if you breathe them in. They're even toxic to animals, plant life as well. There's lots of other side effects as well, like you can make photochemical smog and these kinds of things. But I think the biggest issue is the health implications of breathing it in. In the UK, the largest source of NOx is from actual roadside vehicles. And air pollution in general, not just NOx, but all forms of air pollution, it's responsible for almost 9 million deaths around the world, and it is costing the global economy around $5 trillion each year. If you think, I think that the global GDP is around $80 trillion. It's really significantly impacting our productivity in terms of our economies and the drain on our economies on health related impacts as well as deaths. In 2020, so about 13 years ago, the UK set legal limits on NO2. These are the numbers here. I'm not going to go to the details of the numbers, but essentially at that time, the World Health Organization had agreements with the annual averages that they should be 40 micrograms per meter cubed of NO2. So of the two gases, when we talk about NOx, we mostly focus on NO2 because it's the more toxic of the two gases. Okay, it's about 25 times more toxic than NO. We talk about NOx, but the focus tends to be on NO2. With regards to the UK, unfortunately, we're not meeting those average NO2 levels in a number of locations around the UK. Okay, and we're still trying to find solutions to that. There's lots of things that we've done, like congestion charges, improving the performance of vehicles so they're less polluting, transitioning to electrics, more cycle lanes. We're trying different things, but ultimately we're still above the limits that we set in so many locations, particularly in the bigger cities like London, Birmingham, Glasgow, and so forth. Compounding this challenge, the World Health Organization recently, I think in 2021, they rejigged what they said should be the limit, the annual average limit of NO2. And they said it should actually be about 10 micrograms. That would be much safer. So to make this challenge even more difficult, we've got to get 4 times lower than that if we want to be in line with what the World Health Organization deems safe. And this is a big challenge because this gas, like I've got written here in brackets, it's 0.02 parts per million. Okay, so we're talking about something that's so dilute and we have to somehow get rid of it. And when you have to get rid of something that's already so dilute, it's not trivial. So companies are starting to develop products that use photocatalysts to get rid of NOx pollution from the air. And here are some examples that are already out there, technologies that are already out there. One is by Hydrotech that make these tiles that can remove NOx pollution. Ital Cementi that make concrete, and Kime paint. So this white kind of paint that you can paint buildings with as well. And photocatalysts are getting more and more popular. I think right now the global market value is around 3 billion, and it's expected to grow at a rate of 10% per annum. The interesting thing here is that most products use the photocatalyst titanium dioxide. Okay. So how does that even work? This is where it gets a bit chemistry-like. So titanium dioxide, it's a semiconductor. This is a crystal structure of titanium dioxide on the left, and it's got a bunch of atoms, and these atoms have lots of electrons whizzing around them, and these electrons have different energies because they fill different orbitals. So your GCSE or A-level chemistry is all coming back to you now. And these orbitals all overlap in certain ways, and they give rise to this energy diagram here in the middle, okay? Where you have filled electron environments and unfilled electron environments. And this gap between the filled and unfilled electron environments, you can excite it using light. You can excite these electrons in these filled environments, these unfilled environments. And when you do that, you create an electronic charge in a high energy state. And where it once was, we call it like a positive hole in a lower energy state. And these electrons and holes, they can drive the catalysis that you want to happen, okay? So with regards to titanium, this is a scheme of how it can catalyze NOx on the right. Essentially, these holes in titanium dioxide, they can oxidize ambient water to make these hydroxyl radicals, and these hydroxyl radicals can sequentially oxidize NOx to nitrates. And these electrons can oxidize ambient oxygen in the air to make superoxide, which can oxidize NO straight to the nitrate. But most of the time, you're getting this oxidation pathway that sequentially goes through nitric oxide to nitrous oxide to nitrogen dioxide to nitrate. SmogStop differs in the fact that it reduces NOx. It's not oxidizing the NOx to nitrate. It's primarily reducing it back to nitrogen and oxygen from whence it came. And that's good because it avoids the buildup of nitrate on your photocatalyst, which eventually it will clog your photocatalyst and it won't function anymore. And it avoids this byproduct HONO, which is even more toxic than NO2 itself. So photocatalysts, if they're not performing right, you can actually have a situation where you're making the environment worse than it should be if it's not working correctly. But if you have a photocatalyst that is doing what it should do, then it will make the environment better. And here's some data comparing SmogStop with a traditional TiO2-based photocatalyst. So we've taken the champion, not we, they have taken the champion photocatalyst here, P25 it's called, developed by Evonik, and they've tested it against NOx, and you can see here in red these different cycles of when they've turned the light on and off. And you can see how the NO level drops to about 50% of what it originally was, and then rises again for each cycle, light on and off cycle. But there's a buildup of NO2 as they do that. And that's because you're saturating the catalyst with nitrate, and the nitrate then breaks back down to NO2. So this is a bad thing that you don't want to happen over time, okay? Because it might make the situation more toxic than it originally was. But SmogStop avoids that, and it's very consistent in reducing NO to a similar degree to TO2, but at the same time, you don't get this buildup of NO2. To confirm that, they looked at the surface of the catalyst after testing, and they tested how much nitrate was actually present after the test. And on SmogStop, there was a very small buildup of nitrate. So there was maybe some of this oxidation pathway occurring, but primarily it was the reduction pathway to nitrogen and oxygen, because they were getting 10 times less nitrate than TO2. And they also looked at the potential formation of nitrous acid, and they saw that HONO, nitrous acid, wasn't forming at all during testing of their photocatalyst, which was a relief because it's more toxic than either NO or NO2. And they did some extended weathering. So here, the time goes up to 400 days of weathering, but because it was intense weathering, the 400 days actually represents about 10 years of what would be expected in the field. And they see that the NOx removal rates were roughly around 50% quite consistently across this durability study. So they've made a catalyst that's also quite, it's very important as well if you're going to put it in an external environment that this catalyst is durable to weathering. They tested their catalyst in a range of different lighting conditions. So under just visible light or UV invisible light. They did this because they wanted to see how versatile their catalyst was. Their idea is to use it outdoors for highway barriers, but potentially it could be used under different lighting scenarios. So when the sun sets at night, you're going to have just street lighting radiating on your material, which doesn't have a big UV component. So if it can use visible light as well, that's great. And what they found is that their photocatalyst was able to be activated with visible light as well as UV light. And that differs substantially from TiO2 in that it can only be activated really with UV light. And that's what's unique about this SmogStop composite photocatalyst, in that it's not just containing TiO2, it contains other things patented, can't go into, but it can access more of the solar spectrum, and therefore it has a higher efficiency at converting NOx because it can access more light. So then what they did is they took this photocatalyst and they embedded it within a highway barrier. They took this two-walled highway barrier where the catalyst was placed on the inner wall here, and they developed this barrier to have a certain aerodynamics that will enhance the mixing of gas within the barrier itself. You get a lot of high residence time of the gas along the catalyst as it flows through the barrier, as well as this crank at the top that enhances the dispersion of gas upwards. Okay, so the barrier essentially works in two ways. One, it's a barrier, like it stops the NOx from getting to the other side, and it enhances the upward dispersion of the NOx pollution and mixing with clean air that's at higher levels. So you're basically diluting it with cleaner air that's at higher heights. Okay, but at the same time, you're not just putting that pollution problem elsewhere, because we know that NOx can cause acid rain. And what they've done is they've allowed a portion of the polluted air to go through the barrier, where it's treated by the photocatalyst and converted into something more benign. Okay, by converting the NOx into nitrogen and oxygen. Okay, they've done a bunch of wind tunnel tests, and they found that this double-walled barrier design is more effective than having just a plain barrier, just a vertical barrier. 50% more effective in dispersing the gas. And they did some computational fluid dynamics to understand how to enhance the residence of the gas on the catalyst on the inner wall of the barrier where the catalyst is stored, by adding this little, can't remember what they called it, but yeah, an angled baffle, which will enhance the residence of the gas here so it can be treated by the catalyst. They did some photocatalytic testing of full-scale models in a wind tunnel, and they found that a 5-meter high barrier tested at wind speeds of around 2 meters per second could reduce NOx, well, NO, N2O, and overall NOx levels by 28, 35, and 28% respectively. Okay, and that was essentially by pushing the gas through the top of the barrier here and measuring the NOx levels there, and then at the bottom of the barrier measuring the NOx levels as the gases came out. They did tests in the dark and in the light, and they looked at how the photocatalyst, which is activated with light, was able to convert those NOx gases as it flowed through the barrier. And it was able to treat roughly 1/3 to 1/4 of the pollution as it flowed through the barrier. In Toronto in March 2017, they installed a 15-meter long barrier and slightly taller than in their wind tunnel tests, so about 6.5 meters high. So my understanding is that the barrier is 6 meters high, and then when you add the crank on top, just extra 0.5 meter, the total height is 6.5 meters. And they installed it at this intersection of Highway 401 and Bayview Avenue in Toronto. And it's actually one of the world's busiest highways, with around 340,000 vehicles traversing this 14-lane road every day. They measured changes in NOx level through the barrier between August the 18th, 2017 and February 28th, 2018. Okay, and the full study is here. They placed chemiluminescence analyzers at the top of the crank, so as the gas was coming in, and the bottom of the double wall where the gas exits. And they had an anemometer position 3, where they looked at how the wind was flowing through the barrier. So if the wind was going top to bottom, then they took the top point as, okay, this is the start of the NOx, and this is the end, number 2. And if wind was flowing in the other direction, because the wind direction was changing a lot throughout the study, as you would understand. So then if the wind was flowing from point 2 to point 1 for a particular wind direction, then they would look at the difference between point 2 and 1 to see how the photocatalyst was treating the air. And this is a summary of their results. So they've broken it down to 3 key periods. So between August and September, between September and December, and the full study all the way up to Feb 28th. So there was some points in time where there was roadworks which kind of disturbed the performance of the barrier. They noticed some changes in the barrier performance, mostly because of roadworks maybe caused some particulates to be emitted that maybe blocked the catalyst, and it took some time for it to recover. And also there was a point in time where I'll show you in a sec, where a part of the wall of the barrier was open, like not the SmogStop barrier, but just the highway barrier itself, which made airflows quite different. And when that was closed, it forced the air to go more through the SmogStop barrier, and the performance slightly increased. But essentially, that's more the nitty-gritty of the trial and these particulars. What I thought was encouraging is, despite some of the challenges they saw because of roadworks or closures or whatever, overall the performance was quite good. So for the whole period of the trial, from August 18th to Feb 28th, so around about 6 months of the trial, they saw more than 30% reduction in daytime and nighttime levels of NOx. And it functioned as well at nighttime, like I mentioned to you before, because it's quite well, you can see here, it's quite a lot of street light, and that can function with street light as well. And this is the part I told you about. So this side of the barrier here was open for some of the trial, and then when they closed that, it allowed air to force through the barrier much better. They saw better performance. And this is just a breakdown of some of the data. They saw a variety of wind speeds in different directions. And they noticed that when wind was coming directly from the north-northwest towards the barrier, they saw a better performance. They also, that's what's shown here, that the performance peaked in line with sort of a perpendicular direction of wind. So when wind is going directly towards the barrier, it works best, which is kind of intuitive. And here they've converted the NOx removed into some kind of mass of NOx removed, which they call a mass removal rate. So that's to do with the kilograms of NOx that's removed if you were to have a kilometer stretch of this barrier per vehicle kilometer traveled. Okay. So essentially, you can calculate the mass removal that you would expect if you were to then build much longer stretches of this barrier and actually have an understanding of how much NOx in tons that you're going to be removing from the roads. And you can they essentially calculate that as a proportion of the emissions from that motorway, and what percentage of the emissions will be removed by the photocatalyst or dispersed because of the barrier itself. So just to summarize the field trial, I know that I'm almost at the time, but I'm almost done. So they saw 34% reductions in NOx over the period of the trial. When it was a really sunny day, they saw during particular points in time, I think over a period of an hour, they saw 92% removal of NOx. And here, as I mentioned to you before, you can get around 4,100 vehicle kilometers traveled per kilometer of SmogStop barrier per day. You can remove the pollution from that many vehicles per kilometer of the barrier per day. And they saw that over the period of the trial, there was no loss in performance really of the photocatalyst. I don't know if I show that now. Yeah, I do. I show that now. So this is just after the field trial, and you can see that within the barrier, there isn't much soiling of the barrier itself, and you can see here on the left as well, it looks particularly clean. This was 6 months after the trial, and this is a very recent photograph that Google took from Google Maps, and you can see here it looks quite clean, and that's also very encouraging as well, that you're not going to get this build-up of dirt on the barrier, so it would stop functioning. It's still, after 5 years, I think, of being installed, 6 years now, it still looks very crisp and clean. So it has durability, the catalyst, to maintain its function and retain its cleanliness. Okay. So to conclude, SmogStop developed this unique photocatalyst technology. It's unique in that it reduces NOx to nitrogen oxide, as opposed to oxidizing it, which, from what I've seen, all other commercial products focus on the oxidation of it, which has its challenges. So they avoid that by making this very unique material. And they've incorporated it within a highway barrier. They've done field trials, and it was effective in Toronto, and they're doing trials in the UK. Watch this space, it appears to be effective there as well. And it's been recently endorsed by the Ministry of Transportation in Ontario, which is the title of this talk. That's the first approved pollution barrier that can be used at the roadside. And if you want more technical details of that, I'm sure Steve can give you that information. And that's it. So thank you.
Thank you so much, Andreas. That was such an interesting presentation, and great to hear about the use of photocatalytic technology for dealing with NOx. We've already got some questions coming in, so I'm going to dive straight into those. So thank you so much for that. So the first one is kind of thinking about, so really interesting to see its application for NOx, but it's thinking about its translation to other pollutants. So one of the attendees here has said, the IAQM report on photocatalyst coatings recommended that if further field trials are carried out, they should measure other reaction products. Recognizing what you say about SmogStop not working in the same way as other products, have you included measurements of other pollutants in your field trials?
Okay, so if it were up to me, then yes, I would do that. So I didn't design this particular field trial in Toronto or in the UK and what is measured, but their question is super valid. And in the report I mentioned at the start that I wrote for the Environmental Industries Commission, one of my key outcomes was, yes, we should look at the other potential pollutants that can be formed. So I mentioned nitrous acid, ozone could be formed as well. There could be maybe other VOCs as byproducts. So I mentioned that should also be measured. So I completely agree with them, but I didn't design and implement these particular field trials.
That makes sense. Thank you very much. And moving on, how does the performance as a noise barrier compare with there being an airflow path through the barrier itself?
Question is, I can't answer that. So when I was tasked by SmogStop to review the performance of their barrier, the focus was to be specifically on its use as a photocatalytic barrier, because that's my expertise. When it comes to noise, I think you're going to have to ask Steve about it. So Steve has joined us today from SmogStop, who could maybe answer that question, but that's not something I can answer. I'm sorry.
That's no problem at all. And I was going to mention at the end of this, if there's any kind of technical questions about the product, Steve Barnes from Ground Barriers will be able to answer those questions. So we can direct them to him later on. So thank you for that. Great. So we've got a comment here from Professor Duncan Laxton. He's been working in air quality for 40 years, and he's a fellow of the IAQM. He said, are you aware that DEFRA's AQEG group reviewed the evidence and concluded that photocatalytic surfaces can reduce concentrations close to the treated surface, so that this will not result in significant reductions in NO2 in the surrounding air? Do you believe that that conclusion is wrong? Just to note that the field study, as far as you've kind of described it, does not address this point. Do you have any thoughts on that?
I do have thoughts on that. So I'm aware of that report. That report was published before my report for the Environmental Industries Commission, it's a challenge, isn't it? Because we have a large volume of air and you have only a certain amount of surface that you can coat with this photocatalyst. So you need to understand how effective it will be. Okay, so if you have a very high performing catalyst, but still only treat a very small area within the vicinity of that building or whatever environment, you're going to have really rapid mixing of gases, like the treated air with the polluted, untreated air, and you're not really going to see a significant effect. So if your objective is to purify the air to a certain standard, then you need to understand how you need to be realistic in how the photocatalyst will perform, as well as employ enough of an area of the photocatalyst to be implemented so that you actually do get the result that you want. Okay, so I mentioned earlier about field trials, and very small scale field trials that were done in the UK, I believe in Camden, they didn't result in significant differences in NOx levels because there was too rapid air mixing in a very small area coated. But in larger trials that they've done, I believe in Manila and in Rome, they actually did see significant differences in NOx levels. So it all depends on scale, that's number one. And it also depends on your objectives as well. So every little bit helps. So if, for example, you have your own house or your own building, and you know that there's a product out there that will treat a certain amount of NOx, it will remove it from the atmosphere, it will stop that NOx going elsewhere, other people breathing it in or contributing to acid rain or whatever, then you know that you're going to remove a portion of that NOx every day by having that on your building. So you are contributing to that fight. So it all depends on what your objectives are as well. But yeah, I am familiar with that report. I do know that this is not some kind of silver bullet that's going to solve everything, but you also need to be realistic about how you implement the catalyst as well and the scale that's required to meet your objectives.
That's really useful. Thank you, Andreas. And kind of picking up on a key point that you mentioned there around scale, how easy is it to scale this technology, and what are some of the challenges in its deployment?
Yeah. So different companies are marketing different products. Okay. So there's one company that's marketing sort of a spray coating. So it can be used on like road tarmac, pavements, or even like on ambient sort of building, brick, concrete structures. That's something that can be applied, UV cured, and then it's there for several years and it can be effective. Or when the building material itself is being fabricated in the first place, you can implement the photocatalytic technology within it. So I mentioned Italcementi with their cement, Toto Hydrotect with their tiles, Pilkington NSG with their glazing. So you can have it from when it's being fabricated in the factory, and then it's already incorporated within the building structure when it's installed, or there could be a post-treatment as well. You say, how easy is it? If it's already embedded within the building material itself, that's something that the manufacturer of that technology had to implement in their processes. And from my experience, it's normally something, it's like an add-on that doesn't add a huge markup to their product. Normally it's a very nominal markup, because these catalysts that I'm talking about, they're not made of rare earth minerals. So titanium dioxide, for example, it's quite abundant, it's quite cheap, it's already everywhere. I mean, it's in our makeup, it's in our sunscreen, it's in a lot of our paints already used as a pigment. So it's quite a low-cost technology. And it's not like, for example, catalytic converters in automobiles that require platinum group metals to convert NOx into something more benign. So it uses much more abundant and low-cost materials than other technologies. So it can be used in a widespread fashion in that respect as well, without having to think about supply issues and stuff like that. A little of it goes a long way. It can drive millions of catalytic cycles, you know, without needing to be replaced.
That's really interesting. Thank you. Good to hear about it. Yeah, not needing kind of rare earth minerals for its production. That makes sense. And just to kind of, I think we have time to squeeze in one more question. Thank you so much for today. It's just a more technical question on the kind of study that you did. And it says, I think you said that the barrier can remove NOx from around 4,100 vehicles on a length by length basis. Is that per day? And how many vehicles were using the road in the field trial?
Oh, so that was extrapolated from the study in Toronto. So it was 4,100 vehicles per day. If I go, yeah, for the emissions from 4,100 vehicles per kilometer traveled per kilometer of the barrier installed per day. And I believe along that highway, they get around 300,000 or so vehicles traversing it per day. So it's a portion of those vehicles. What you also have to understand as well is that that was a very multi-lane highway, and this was installed at just one at the end of that lane of the highway as well. So it would really only be able to treat the pollution in the lanes close to it. Okay, but that's significant, isn't it? Like, so if you're going to install a kilometer of this barrier and it removes the pollution from 4,100 vehicles entirely, then that could be significant enough to reduce your NOx levels so that pedestrians behind the barrier are now breathing in NOx levels that are now within the regulations that you've specified you would meet. So, like I said to you before, I don't think that there's any technology out there that could just suddenly remove parts per million NOx completely. But there's technologies out there like this that can help remove significant amounts to help you then be in line with your legislative standards. So that's my take on that.
That's so useful. I think that's all we have time for today. So I'm sorry to any attendees whose questions I didn't get to. As I mentioned before, any other follow-up questions, please do direct these to Steve Barnes, who's Business Development Manager at Ground Barriers. And a massive thank you to you, Steve, for helping organise this event. And of course to you, Andreas, for presenting today. It's been so interesting to hear your presentation. So thank you very much.